Okay, we just calculated the percent dissociation of 0.1 molar acetic acid, and that percentage was 1.34%, and that was a lecture from chapter 14. So that was just kind of a quick review. We're going to use it to compare now what happens with, now number 2, what would be the percent dissociation of a mixture containing 0.1 molar acetic acid and 0.1 molar sodium acetate. Again, common mistake. People want to go, okay, I've got acetic acid, sodium acetate, and they want to add them together over on the reactant side. That's not okay. You're not going to do that, because I've got acetic acid, which is a weak acid, and this acetate ion is the conjugate base, so that means they need to be on opposite sides. But if you think about something that's good for you guys to do when you're dealing with these problems, and you know, these look similar to our equilibrium problems, but as we get into buffers and stuff, it'll be good for you to kind of, I like to say, just like get into the beaker and see what's in there. So if we have acetic acid, I have HC2H3O2 in my beaker, and it's not, most of it is still together. It's not dissociated because it's a weak acid. So in the beaker, it's mostly going to be like this. I also have the sodium acetate. When I put that in the beaker of solution, then it is going to separate into ions, sodium ions and then acetate ions. Okay, so I'm getting into the beaker and I'm seeing what's there. Kind of like figuring out if salts are acidic or basic. We can cross out things depending on if they come from a strong base or a strong acid. So right away, I can look at these sodium ions and basically say that they don't matter. When we're talking about pH or dissociation or anything like that, sodium ions don't matter, just like they didn't matter for pH of salts. So what I'm working with here in this reaction is I'm working with acetic acid. I'm working with these acetate ions. And so basically, I'm just going to have a normal dissociation reaction of acetic acid, H+, some H+, right? Not a ton, but a little bit. And then acetate ions. And all the while I'm trying to calculate the percent dissociation here. So let's see, the difference here, it's calculated exactly the same way as you did from number 1. The difference is that not only do I have the initial concentration of acetic acid to be 0.10 molar, I also have an initial concentration of 0.10 molar of acetate ions. And you guys actually did this in a free response question. You did it a week or so ago. You just didn't know you did it. But you were given a salt that was added to solution, and so you just had to put that as your initial concentration. So this is the only difference to problems that we did in chapter 14, is that you're not starting with 0 of this over here. You're starting with a certain concentration. Still 0 hydrogen ions as acetic acid begins to dissociate. So then I'm going to have my plus x, which gives me 0.10 plus x, x right there, minus x. Okay, my Ka is 1.8 times 10 to the negative 5 equals x times 0.10 plus x over 0.10 minus x. Now you guys should be good at solving for x by now, but you should see on this that x is equal to 1.8 times 10 to the negative 5, which gives me a percent dissociation. If I take this, my x is equal to the hydrogen ion concentration. I should always get in the habit of writing that out so that you see that as you go back through the problem. And my percent, then I would take my 1.8 times 10 to the negative 5 and divide it by my initial concentration of acetic acid, which was 0.10, and then times it by 100. Some of you guys forgot to times by 100 on your test Wednesday. Gives me a percentage of 0.018%. Now, you don't have to write this down, but if we compare those numbers, without the salt being added. The percent dissociation was 1.34. When I added the sodium acetate to it, it changed the percent dissociation to 0.018, because if I'm adding this, then I'm adding concentration of a product, so I'm shifting the equilibrium to the left, producing also less hydrogen ions. So what you should write down, number 5 here. When you add more common ion, so we'll say adding more common ion means less dissociation of a weak acid. Okay. That's the common ion effect, which basically gets you into the introductory idea of what a buffer is and how it works. So let's talk just about some general stuff about buffers and what buffers are made up of and how they work, which we kind of actually already talked about how they work. It's because of the common ion effect that they're able to resist a change in pH. So go ahead and copy those down for a couple of minutes. Okay, a buffer is a solution that resists a change in pH, and it has to do with the common ion being present, like adding a salt that matches up the conjugate base of the weak acid, if it's a weak acid buffer, because it does not allow as many hydrogen ions to be produced, and so the pH does not change as much, because pH is, we know, dependent on hydrogen ion production. And so things that a buffer must have. If you are identifying a buffer, it's got to have either a weak acid and a significant quantity of its partner, which means its conjugate base. Okay, like weak acid, acetic acid, its partner would be the acetate ion coming from some kind of salt, like sodium acetate. Or a weak base and its conjugate acid partner. So they could be made up of acidic solutions or basic solutions, these buffers. Again, they're resisting a change in pH. A very common example would be our blood in our body is a very important buffer. It does not change pH very easily. It has a very stable pH, which is good, because if it didn't, then, you know, if you drink a soda or something which is very acidic, then it would also change the pH of your blood if it wasn't buffered and it wasn't able to kind of handle that. So what do I mean when it says a significant quantity of the partner? Significant quantity means within a factor of 10, which just means if my concentration of weak acid is 1 molar, then my concentration of the conjugate base has to be anywhere from 0.1 molar to 10 molar. So within a factor of 10, either below or above. And an ideal buffer has the same concentration of both.